See, so we were starting with this basic idea that our EMF here that we saw, this is Faraday's law, that our EMF is equal to the negative of our changing flux. So the rate at which our magnetic flux changes, the negative of that will be our EMF. Remember this magnetic flux, this is that integral of B dot dA, which is what we've done this before, where we figure out what is the flux to a particular surface. So you'll see some more of that coming up, and you'll see it in the homework as well. So this is our EMF. We had this graph where we looked at where is the EMF the smallest and the biggest, and the EMF is not really dependent upon the magnitude of the magnetic field, but it's dependent upon how that magnetic field changes, how quickly it changes. And the more it changes, then the more EMF that you'll get. And we saw that with the coil of wire. Sorry, I think I left the music on. Let me get rid of it. Sorry about that. So the EMF is not dependent upon the magnitude of the magnetic field. Like here we have a really big magnetic field, but no electromotive force here because the magnetic field is not changing, so the flux isn't changing. All right, so that derivative d phi dt is equal to 0. We did this simple example, and I realized I went back and looked at this. There is this one thing that we haven't seen before, which is the magnetic field of the solenoid. It's because we didn't do Ampere's law. I decided to skip over Ampere's law, and you needed that to derive what is the magnetic field of the solenoid. But otherwise, you could see this actually on the test. I think I mentioned last time that you might not, but you could see something like this. The idea here is that I have these two coils, and then one has a smaller coil inside of the bigger coil, and the magnetic field of the bigger coil, that's the blue coil here, is equal to this value. Now I'll give you this if you need it, so don't bother memorizing this, but I'll give it to you in the problem if you need it. Or I'll just give you what is the initial or the final magnetic field. Let's try this. So this magnetic field changed because my solenoid, that's the blue coil here, the one on the outside, it started out with a certain current in it. And so the magnetic field is this mu naught times that current times the number of turns per unit length. The magnetic field started out at some non-zero value and then it decreased. And because of that, we were able to determine what was the change in flux. And then because we could figure out what was the area, right, so here's our magnetic field. This is our area, so we're just calculating that flux, that integral of B dot dA. Right, where our area vector is just the cross-sectional area of that solenoid. This is our magnetic field in the solenoid, and we figure out what is our flux here. That's our initial flux, and then our final flux was 0 because it goes to 0. And then our dt term here is just the time that it takes to decrease. And then that gives us the EMF that's produced right here. So this is our EMF. And then further, we had the number of turns, which is 130. And so our Faraday's law here is our minus n times dt dt. So we'll just multiply that times n in order to get the maximum EMF. Okay? So you could see, we're going to see several types of problems involving Faraday's law, but you could see one like this on the test where you just change the you change the current inside your coil. That changes your magnetic field, which further changes your flux. Make sure you know how to calculate that flux, that integral of B dot dA, which in practice is really just going to be our magnetic field times the area vector. And then also know how to apply Faraday's law in this case. Figuring out our change in our flux divided by our change in our time. And that gives us our EMF when we multiply times again. Okay? Make sure you start taking a look at the homework. I've mentioned that on Friday. I expect not many of you have. And I understand, but you need to start looking at it soon because you'll need to spend some time on the homework to be prepared for the exam. So I go ahead and start looking at that today, tomorrow. Okay? How many of you have finished it already? Or the first two probably? Start looking at it? You don't have to answer. Don't answer that. Yeah.
The homework for chapter 6 isn't directly behind the chapter, so
I know, it's all sort of mushed together. So chapter 6 and 7, just sort of the way I did it, I just mushed it together. So you're just looking at the first 2 questions so far. Is that clear?
okay.
I can tell you which ones if I can see.
Yeah, sure.
So right now you should get right here. So chapter 6 and 7, you should be looking at, after today, you should be able to do 1, you should be able to do 2. We're going to do probably somewhere to that. 3. Yeah, you should be just be able to do 1, 2, or 3. There's not a problem like this, but make sure you look at this example and consider it. It's on page 241. Okay? Then we started looking at Lenz's law, and Lenz's law will tell us the direction of the induced current. So if we have an EMF, an electromotive force, then we're also going to have a current. So we'll have a loop of wire with an EMF set up inside of it, and then we'll also have a current. And we looked here at a couple of examples regarding how to figure out the direction of the induced current. Lenz's law basically says that the induced current will produce a magnetic field that's opposing the direction of the changing magnetic field. I'll sort of give that to you in a little more usable term here in just a second. But we're going to oppose the change in the magnetic flux. And then we look here, for example, if I have these magnets moving in this direction, north, south pole, then I'm going to create an opposing magnet over here with my induced current that has a north-south pole in this direction. And then once we know the direction of the magnetic field, then we can figure out what is the direction of the induced current that caused that magnetic field. That's going back to our right-hand rule, where if our magnetic field is in this direction, that means that my current is coming out like this. So at the section of this loop toward here, it's going to be going down the current. Are you with me so far in this? Yeah. We'll do some clicker questions here in just a bit. And then if we have a south-north pole moving in, then our south pole is in this direction, so we'll have another south pole due to this induced current that's in the opposing direction. So my induced current is always going to oppose any change in flux. And we're going to look at it in a slightly different way. We'll get the same answer, but it'll be more useful when we're actually looking at problems. And that's looking at the opposition of flux change. Okay, so the B field, the magnetic field, due to the induced current, so I'm going to call this BI. I is for induced. So this is our induced magnetic field. And it's due to this induced current, which remember is due to this induced EMF. So I have this changing magnetic flux that's inducing an EMF, which is inducing a current. And then because a current causes a magnetic field, then we have an induced magnetic field. So we have several steps here. We're inducing an EMF, which causes a current, which induces a magnetic field. So the magnetic field due to this induced current will oppose a change in the magnetic flux. That change in that magnetic flux is, our phi. So I think this is best done with some examples. So let's imagine, so what do I have over here? So let's imagine that I have a coil of wire, and I have a north and a south pole. Now we've already said that if I move this north-south pole in this direction, that it's going to cause a north-south pole in this direction. So if my velocity, if I'm moving this, V is in this direction, that means that I have a magnetic field over here in this direction, which means that I will have an induced magnetic field in this direction. That's what I've had before, right? It's always going to oppose a change in the magnetic flux. And further, this magnetic field, which is due to the magnet, is it increasing or decreasing as I move this magnet into this loop? Is this value increasing or is it going to be decreasing as I move this magnet into this direction? Going up or down? Magnet's getting closer, magnetic field's going to do what? It's going to go up, right? So magnetic field, or the magnetic field due to this magnet is increasing. All right, now let's imagine instead I have a loop. I have the same north-south magnet, but in this case, I'm moving it in a direction like that. Okay, so it's as if I've had it inside the coil, and now I'm pulling it away from the coil. Now, my magnetic field is still, excuse me, in this direction. I'm sorry, when I go to Mississippi, I sort of keep my accent, and then, like one day I was there, and my daughter, I forget what I was saying, it's like, go tell your mom, or go tell your mama, or whatever, to someone or whatever, and my daughter looked at me, she's like, that's not even a word. Go tell your mother. All right, so anyway, here, my magnetic field here, when I'm pulling that magnet away, is it increasing or decreasing? It's decreasing, right. So when that magnet is going away, this magnetic field is decreasing. So remember, this induced magnetic field, the one that we come up with Faraday's law, it's always going to oppose a change in the magnetic flux. So here, if my magnetic field is decreasing when I pull this magnet away, what do you think the direction of my induced magnetic field will be? Will it be to the left or to the right? It's going to be to the left, because I always want to oppose any change in the magnetic field. And so when this begins to decrease, when I pull this magnet away, then I'm going to cause an induced magnetic field, Bi, in this way. So let's put that in words. Our induced magnetic field, in this case, it is in the same direction as B, because B is decreasing. Over here, Bi opposes B because B is increasing. So always that induced magnetic field will oppose any change in flux. If the flux is increasing, then Bi will oppose the direction of it. If the flux due to B is decreasing, then Bi will be in the same direction as the magnetic field. It's always going to fill in the gap, basically. It always will oppose the direction of the magnetic field, of the changing flux. So let's do one more. Let's imagine, what if I have a coil? I have a south magnet, a north pole. Let's say that this is moving, I don't know, in this direction. So we're moving it at a certain velocity in that direction. What will be the direction of the induced magnetic field over here? Will it be A to the left or B to the right? What is the direction of Bi? A to the left or B to the right? Think about what is the direction of the magnetic field caused by this, and then is it increasing or decreasing? If it's increasing, then the magnetic field induced, that's Bi, will be opposite. If it's decreasing, it'll be in the same direction as this. So what is the direction of Bi? To the left or to the right? We're split evenly on left and right. What is the direction of the magnetic field due to this magnet? Is it in that direction or this direction? Remember, the magnetic field will run from south to north. So the magnetic field B is going to be in this direction. All right, the magnetic field due to this magnet, this bar magnet, is in this direction. It runs from south to north, a magnetic field. All right. Okay, let's see. I'm going to pause. I'm going to stop here. I'll stop at 1:30. So let's take a look. Is this increasing or decreasing when I pull this magnet away? This magnetic field is decreasing. Right. So my magnetic field here, B, is decreasing. So is BI, is it going to be in the same direction or the opposite direction of B? Don't answer that. But you want to ask yourself the question, is BI going to be in the opposite direction or the same direction as B? Now B here is decreasing. The magnetic field induced by this current in the loop is going to be always in the direction opposite, opposing a change in the magnetic field here. Let's try it again. Okay, we'll just close this. Try it again. Is BI going to be opposite direction or the same direction as B, since B is decreasing? Okay, a lot better. I'm going to stop at 20. Okay, good. B is right. Yes, that's right. So our magnetic field here is to the right. That means since it's decreasing, BI is in the same direction. So BI then would be, now right over here, the magnetic field due to this coil is going to be in that direction. All right, and then once we know that, and we'll get into this in the concept test in just a few minutes, but once we know that BI is in that direction, then we can determine what is the direction of the current in the loop. Let's flip it. So I'll take this and sort of put it in the plane of the page. BI is out of the page. So what I've done is I've just taken this and I've flipped it so that this current is this magnetic field is coming out of here. And we want to figure out what is the direction of the current. We do our right-hand rule. It's going to be like this. So our current here is flowing in this direction in a counterclockwise fashion. So I have a current flowing through that loop. Or you can think of it as my EMF acting in that loop. Or as we'll see later, it's actually an electric field that's being induced in a counterclockwise direction. All right, we'll take a look at, let's do an example first, how this comes up, and then we will do some more clicker questions. So what is the magnitude and the direction of an induced EMF in this loop, which I'm going to draw for you, at 10 seconds? So what I have is I have a battery. Battery is at 2 volts. And I have a loop of wire. The loop of wire has a radius of 0.2 meters. And the loop of wire sits in a magnetic field.
Is this information you would give us, or?
Yeah, I'm sorry. When I made the notes, I just didn't draw the figure.
Oh, okay.
So I'm just drawing the figure for you here. Okay, so I have a loop of wire. The loop of wire has a resistance of 2 ohms. it sits inside of a magnetic field that's out of the page, coming towards you, and this loop of wire has a radius of 0.2 meters that sits inside that loop, that sits inside that magnetic field. The magnetic field changes at this rate, so this is just a function that describes how the magnetic field varies with time. So if you have the magnetic field at, say, 1 second, then you would say 4 times 1 squared plus 2 times 1 plus 3. So for example, at 1 second, this would be 6.9 Tesla. But it changes with time. So now I want to know at t equal 10 seconds, what is the magnitude and the direction of the induced EMF? All right, so I first begin with Faraday's law. So what we've been working with, that's that the EMF that's induced is equal to, well, we're just going to leave the negative off for now. We're just looking for the magnitude. So we'll just say it's equal to d phi dt. That's the change in the magnetic flux. Remembering that T, my magnetic flux, that's the integral of B dot dA. But again, in practice, this is really just B times A, because we're looking at an area, or we're looking at a magnetic field that is not dependent upon the area. So this B just comes out, and so the integral of A is just equal to, the integral of dA is just equal to A. So just like we've done before, finding that flux is just the product of the magnetic field and the area. All right. Now we'll do a look at our magnetic flux, or excuse me, our EMF is going to be A times dB dt, because A doesn't change with time. Let me put some of these in words. So here we're assuming B is not dependent on A. So the integral of B dA is B times the integral of dA, which is equal to B times A. So that's how that integral gets simplified. Further, we're also assuming, and that's the case here, is that B and dA are in the same direction. And that's why B dot dA is equal to B dA. That our dot product, we don't need to do our dot product. Well, we do it, but they're in the same direction, so I just get rid of that. Okay? And then further down here, we're assuming, when I write this, we're assuming that A does not change with time. So we would say d phi dt is equal to d BA dt. But since A doesn't change with time, we can just write it like this. So several assumptions we've made so far, and they're fairly safe assumptions, but D and dA are in the same direction, so our dot product goes away. D is not dependent upon A, so this interval is just the product of D and A. And then also that A doesn't change with time. So we'll see, I think we'll see actually, that you can have A change with time. So you can have a loop inside a magnetic field, and instead of changing the magnetic field, you can change the area. We talked about this actually. If you change the area, you'll still get that induced EMF. Okay, you'll have homework problems like this, so you should certainly practice these. You'll probably see one like this on the test. Okay, so now, with that said, let's return back to this problem. So we have E is the area. This area is going to be pi r squared over 2. It's a semicircle. So it's pi r squared, that's a circle, divided by 2, that's a semi, half a circle, times the derivative dB dt. So what is the derivative of this function? Now remember your derivatives, right? Polynomial derivative. 2 times 4 times t to the 2 minus 1. So it's going to be what? 8t plus 2. Right, 8t plus 2. the 3 goes away, the derivative of a constant is 0. So I get 8t plus 2. I'm looking for it at 10 seconds. I get pi times 0.2 meters, that's the radius of my semicircle, squared divided by 2 times 8 times 10 seconds plus 2. And that works out to be 5.2 volts. Okay, you have a couple different problems where you're looking at this, where you have the magnetic field is changing as a certain function. You have to take the derivative of that function and figure out at a particular time what is the rate that it's changing at. Now, we haven't answered the question of what is the direction. Well, and by the way, this is just the induced, this is the induced voltage. But if you notice up here that we already have an actual voltage of 2 volts. So the answer here for what is the voltage that's induced in this, or what is the voltage across this loop of wire, could either be 7.2 or it could be 3.2. It depends on the direction of our induced EMF. Does it oppose this 2 volts or is it in the same direction as this 2 volts? So we need to figure out, as this magnetic field is changing, what is going to be the direction of the induced EMF. So it's a pretty important question to figure out what is the direction. Let's consider that. And then once we get that direction, we can figure out what do we need to add or subtract this 5.2 volts to the 2 volts. All right, so at t equal 10 seconds, the flux is in the plus z direction. I know that for a couple of reasons. I'll put it in parentheses. First of all, I show in the figure that initially the magnetic field is out of the page. Also, at t equal 10 seconds, the magnetic field is positive. Go back to this function. We have this function. Right now, at t equals 0, the magnetic field is out of the page. And right now, at t equals 0, the magnetic field has a value of what? It has 3 Tesla. 4 times 0 plus 2 times 0 plus 3. At the initial condition, I have 3 Tesla. Now, because all these terms are positive, they're always going to be in the same direction. But if you have a term that's negative, then you might you will have a time, actually, you might have a time when the magnetic field goes negative. Okay? But for this one, the magnetic field is always going to be in the plus z direction. And so we're really just looking at t equal 10 seconds. Now, if at 10 seconds the magnetic field was negative, then we would say it's in the negative z direction. But for this case, I think maybe in your homeworks too, that the magnetic field is out of the page. It's in the plus z direction. Is it increasing or decreasing the magnetic field? Or is the flux increasing or decreasing? And you want to ask yourself the question, is the flux increasing or decreasing? And remember, that's an important question, because if it's increasing, then the induced flux will be in the opposite direction. If it's decreasing, it'll be in the same direction. So is the flux increasing or decreasing? How would we determine that if the flux is decreasing or increasing? Okay, yeah, we can think about the final mass initial. What could we? Well, we could, but we could look at what we have already and determine if it's increasing or decreasing. Have a positive value. So that means it's what? It's increasing. Since my derivative is positive, that means it's increasing, right? If I have a positive rate of change, that means it's increasing. If I have a positive derivative, it means it's increasing. So since d phi dt is positive, the flux is increasing. Since d phi dt is positive, the flux is increasing because my rate of change is positive. If it were negative, it would be decreasing. Okay, so we've got it in the plus z direction, and phi is increasing. So, by Lenz's law, the magnetic field the induced magnetic field is what? Is it out of the page or into the page? Let's do it as a clicker question. The B field is either A, out of the page, like that, or B, into the page. What is the induced magnetic field? Is it going to be out of the page, A, or is it going to be into the page, B? Now remember, initially, we had it out of the page. But now I want to know, is the magnetic field now, the induced magnetic field rather, let me go back. Initially, the magnetic field that was there is out of the page. Now we're asking about the induced magnetic field. Is it going to be out of the page or into the page? Okay, good. All right, so we'll stop at 52. Good, B is right. It's going to be, because the magnetic flux is increasing, the induced magnetic field will be opposite the direction of the actual magnetic field. So it's going to be B, because d phi dt is positive, and B is out of the page. So it's going to be opposite that. BI is opposite that. Ainsley?
Would BI also be increasing in the opposite direction, or would it just be like that?
It would be decreasing in the opposite direction.
Decreasing.
Well, let's see. Yes. Yes, it will be decreasing. It will do the opposite of whatever B is doing. So, well, no, let me take that back. So, it would be increasing in the opposite direction because the flux is going to continue to increase in the opposite direction. So BI will also continue to increase in the opposite direction. You follow? Yeah. Okay. All right. So here our flux is out of the page. So we just need to imagine our loop here. Our loop is generating a magnetic field that's like that. This is BI, and now we need to know what is the direction of the current. Well, gosh, what is it? Is it going to be clockwise or counterclockwise? Is the direction of the current going to be clockwise, or is it counterclockwise? The direction of the current. Clockwise or counterclockwise? And then also, not just the current, but we're thinking about the EMF as well as what we'll talk about later, the electric field. All those will be in the same direction. Is it going to be clockwise or counterclockwise? Go back to our previous chapter. Our magnetic field is into the page. Our thumb will give the direction. Is it going to be clockwise or counterclockwise? Okay, y'all doing great. Stop at 40. Okay, 40. A is right. My magnetic field, remember my fingers go into the page here, and it gives my thumb in this direction. Oh, I see, you might have used that. I'll have to think about that. I don't know if I'm pretty sure that you use the flux inside the loop. I'll think about that. That's what y'all are thinking, right? If you put that opposite answer, that if you imagine, well, the magnetic field is here, then you get an opposite direction. Yeah.
So the initial magnetic field that we have is still here, right? So it would be just opposing with the one that you created.
Right, yeah, you still have that magnetic field there.
And then on the inside, it would be stronger than on the outside, so it would be strong enough to like negate it on the inside, but it would still feel the opposite on the outside.
I think so, Cody. I'm not sure. I'll have to think about it. I'll get back to you next time. But for right now, we'll just take the current. We'll consider these magnetic field lines, and that's going to give us a current that is in that direction. I'll have to think about it. I'm not sure. Okay? So just think about the current or the magnetic field inside the loop. It has to do with solenoids. I'll have to go back and take a look at it. Y'all follow me so far? All right, so if our current is in that direction, if we go back and imagine what our loop was, remember our loop was actually part of a bigger thing, and it had a battery that looked like this. Now this drives a current in this direction, so this is our induced current. So am I going to add or subtract that 5.2 volts? Right, so I'll take the difference in those two. So my actual EMF will be the difference in 5.2 and 2. I'm just going to take the absolute value of it, which is going to be 3 volts. Or 3 volts. The reason I'm doing that is because my two currents are opposing one another, or my two EMFs are opposing one another. And so then if I want to figure out the current in the loop, which is actually what the question is asking, that current is going to be V over R, which is going to be, it should be 3.2. 3.2 divided by 2 ohms, which is going to be 1.6 amps. Okay? That current will be clockwise, by the way, because this is the bigger EMF pushing current in this direction. This is our 2 volts. This is our 5.2 volts. So it'll be in the clockwise direction. We'll see some similar questions to this next time. We're going to have to wrap up here in just a second to do evals. But look in the homework, because there are several similar problems to this, and you'll see some on the test as well. For sure. You'll definitely see one like this. But several problems in the homework to help you practice this. Okay? One more thing. This is pretty straightforward. We have a few more minutes. So, if we have an induced current, then we're also going to have an induced electric field, because induced currents are caused by electric fields. All right, so a changing magnetic field produces an E field. So we saw that with Faraday's law, right, that E is equal to negative d phi dt. That if we have a changing B field, that's this, our changing magnetic flux, that causes an EMF, that's this, and also a current, because an EMF set up in a wire will cause a current. But actually what it's doing is not causing a current directly, but it's causing an electric field. In fact, whenever we have a current, it's because we have an electric field that's inside of our wire. But it doesn't matter if we have the wire or not, that we cannot still have an electric field. So, for example, if we have a magnetic field, it looks like this. And let's say it's an increasing magnetic field. It's an increasing B, which also means, by the way, an increasing flux. All right, because our flux is dependent upon our magnetic field. In this case, it's going to cause, if we had a loop of wire, it would cause a current in this direction. I'll let you go back and think about that, the direction of it, but the current will be in that direction. And then we can also think about the electric field is also in this direction. So the electric field will always follow the direction of the current. Or really, it's the opposite of that, but the current follows the direction of the electric field. That whenever I have a current, it's because I have and electric field. So we can think about it further and not even draw the current. That if I have this changing magnetic field that's increasing, then I have an electric field that goes like this. So not even thinking about currents, just thinking about electric fields. We'll see this later when we get into inductors, this idea of a current for it. Yeah.
I'm confused about the direction of the current, like on that top one.
Mhm.
Did we just have that situation it went the opposite way?
Well, let's see. Did we? You're right. Yeah, it is the opposite direction. Sorry about that. So, double check that's right. So if we have our increasing magnetic field, that means that the induced... Oh, no. Yes, you are right. So here, sorry about that, the current is actually in the opposite direction, and the electric field is also in the opposite direction. Okay? Is that clear? All right, well, let's wrap up there. We're going to do evals. Have about 10 or 12 minutes to do evals. I've done these before. You know how to do them. All right. Just to remind you, there are a couple different things in here. I will need to try and take this to the college office. That is. But you have a couple things. This, you have this form, which we need to do with a pencil. You want to need a pencil? Not have a pencil? I don't do that. Yeah. All right. So these, fill these out. The process. When I get the numbers back, they are useful. I do look at them very good, so we'll see how things are going in the class. Our administration sees them as well. And then these are open comments. These are useful if you want to see changes in the course. I don't want to affect you, but it will affect next semester. So if you want to see changes in the course, this is useful. Nobody else sees this. They seal it back up in the envelope and send it straight back to me. So if you have something that you want to write about the course, that's fine. Of course, I won't see them until after you get your grade. So if it's critical or whatever, that's great. I like to have critical comments, okay? Any questions about this? Please take time. I'll go over them. Somebody can take them over to the dean's office for me. We don't want this.
And did you say?
Did you say that? Thank you. Instructions are here. When you write the number on the board. Claire, we hand those out to the class. And Devin, you'll hand those out. And on there, you'll need to write the CRN number. This is CRN 10662. CRN 10662. I'll be out of here in just a second. A few little things to take care of.